Deep within the constellation of Cygnus lies a stellar monster that has completely rewritten our 2025 understanding of stellar physics. Using cutting-edge detection methods unavailable just years ago, astronomers confirmed hypergiant size revisions that push our models to new limits. The largest star size record was rewritten when new measurements shrank UY Scuti from 1,700 to about 1,400 solar radii, while next-generation solar observations revealed unprecedented dynamics in our own star's behavior. Meanwhile, neutron star collision simulations, using 2025's advanced computing power, have unveiled new insights into the densest objects in the universe. The implications of these discoveries are so profound that they're forcing us to reconsider basic principles of astrophysics itself. But one particular detection would soon emerge that challenged not just stellar models, but the very foundations of cosmic physics. The detection that changed everything. The first anomalous readings appeared during routine observations conducted by the Gemini South Observatory, working in conjunction with the Very Large Telescope's interferometry system. Dr. Sarah Chen, leading the night shift at the Chilean facility, noticed something peculiar in the spectral data streaming from the Cygnus region. The wavelength patterns emerging from coordinates 20H12M 30.5s showed characteristics that didn't align with any known stellar classification system in the astronomical databases. What made this detection revolutionary was the combination of technologies that weren't available to previous generations of astronomers. The VLT's interferometry capabilities, enhanced with adaptive optics systems, can compensate for atmospheric disturbances with unprecedented precision. High-resolution measurements revealed angular diameter discrepancies that challenged existing size estimates for hypergiants in the region. These systems identified the Cygnus object as requiring immediate follow-up study due to its unusual characteristics. The confusion began immediately when research teams attempted to classify the object using standard stellar taxonomy. The temperature readings suggested a main sequence star, but the luminosity measurements indicated something far more massive. The spectral lines showed hydrogen and helium absorption features typical of normal stars, yet embedded within this familiar pattern were absorption signatures that defied conventional interpretation. Team members at the European Southern Observatory ran the data through multiple analysis programs, each returning conflicting results about the star's fundamental properties. Independent teams from Gemini South and Hubble reobserved the star, confirming consistent measurements and ruling out instrument error. The Subaru telescope in Hawaii captured identical spectral signatures during their observation window. Radio telescopes in Australia detected unusual emission patterns from the same coordinates. Every facility using different telescope designs and detection methods recorded identical anomalous readings from the target star. The first major revelation emerged when detailed spectral analysis revealed absorption lines that challenged current models of dust-enshrouded hypergiants. Unlike VY Canis Majoris, whose complex dust envelope affects radius estimates in predictable ways, this star exhibited spectroscopic features that seemed to shift depending on observation wavelength. The dust interaction patterns suggested a stellar environment unlike anything previously catalogued, with material distributions that defied conventional stellar atmosphere models. Word of the discovery spread rapidly through the international astronomical community via secure research networks. Scientists who had devoted their careers to stellar physics found themselves confronting data that challenged fundamental assumptions about how hypergiants maintain their structure and interact with surrounding material. The excitement was palpable, but it was tempered by a growing sense of unease as researchers realized they were observing something that pushed stellar physics models to their absolute limits. Emergency coordination meetings were convened by NASA, the European Space Agency, and other major space organizations within 2 weeks of the initial detection. These closed-door sessions brought together leading astrophysicists, stellar evolution specialists, and theoretical researchers to discuss the implications of the findings. The meetings remained classified, but leaked reports suggested that participants were divided between those who believed the observations represented a breakthrough in hypergenic research and those who suspected systematic errors in the measurement techniques. The significance of this discovery cannot be overstated in the context of modern astrophysics. Throughout the 20th and early 21st centuries, stellar astronomy had evolved through incremental improvements in our understanding of stellar structure, nuclear fusion processes, and evolutionary pathways. Occasionally, discoveries like neutron stars or black holes required adjustments to existing theories, but the fundamental principles governing stellar physics remained consistent. This object represented the first time in decades that a single stellar observation forced scientists to question basic assumptions about stellar behavior. As observation campaigns continued through late 2025, each new dataset revealed additional anomalies that deepened the mystery. The star's luminosity varied in patterns that didn't correspond to known pulsation modes or binary interactions. Its magnetic field strength, measured through Zeeman splitting of spectral lines, exceeded theoretical maximum values for stellar magnetic fields by several orders of magnitude. Most perplexing was the discovery that different wavelength observations seemed to reveal different stellar properties, as if the star existed in multiple states simultaneously. The international astronomical community found itself grappling with observational evidence that challenged not just stellar evolution models, but fundamental principles of stellar structure and behavior. Computer simulations attempting to model the observed properties consistently failed to produce stable stellar configurations. The star's existence seemed to violate multiple established principles simultaneously, yet independent observations confirmed its reality beyond any reasonable doubt. Research teams began exploring increasingly exotic explanations for the star's properties. Some proposed that the object represented a completely new category of hypergenic, possibly formed through unknown processes involving extreme stellar winds and mass loss. Others suggested that the star might be undergoing evolutionary phases that current models couldn't predict. The most radical hypotheses proposed that the observations might represent evidence of stellar physics operating under conditions never before documented. The implications extended far beyond stellar astronomy into fundamental astrophysics. If this star's properties could be verified and understood, it might provide insights into stellar evolution, mass loss mechanisms, and the limits of stellar stability that could revolutionize our understanding of massive star behavior. The discovery suggested that hypergenic stars could serve as natural laboratories for testing physical theories under conditions impossible to recreate in terrestrial environments. What emerged from months of intensive observation was the realization that this star challenges our understanding of stellar evolution, while simultaneously questioning established models of how matter behaves in extreme stellar environments. The object's mere existence suggests that stellar physics operates under principles more complex than current scientific frameworks can accommodate. Each new observation revealed additional layers of complexity, building toward revelations that would force astronomers to reconsider fundamental assumptions about stellar nucleosynthesis and the very processes that power the universe's most massive stars. Impossible nuclear fusion signatures. The spectroscopic data revealed something that should not exist according to every nuclear physics textbook written in the past century. This star was actively fusing elements that require conditions so extreme they violate the fundamental principles governing stellar cores. The wavelength signatures showed clear evidence of nuclear reactions involving superheavy elements with atomic numbers exceeding 120. Elements so unstable they decay within microseconds under laboratory conditions, yet somehow maintaining coherent fusion processes within this stellar environment. Understanding why this discovery represents such a profound challenge requires examining how stellar nucleosynthesis normally operates. Stars generate energy through nuclear fusion, beginning with hydrogen atoms combining to form helium in their cores. This process requires temperatures around 15 million degrees Celsius and pressures 250 billion times greater than Earth's atmospheric pressure. As stars age and exhaust their hydrogen fuel, they begin fusing helium into carbon and oxygen, then progressively heavier elements up to iron. Each step demands higher temperatures and pressures, with silicon fusion requiring core temperatures exceeding 3 billion degrees Celsius. The fusion chain typically stops at iron because fusing elements heavier than iron actually absorbs energy rather than releasing it. This fundamental principle explains why stars cannot naturally produce elements heavier than iron through normal fusion processes. Elements beyond iron are created during supernova explosions or neutron-star mergers, where the extreme conditions briefly allow rapid neutron capture processes to build superheavy nuclei before they decay into stable heavy elements like gold and platinum. Yet the spectral analysis from this anomalous star showed active fusion signatures for elements well beyond the theoretical limits of stellar nucleosynthesis. The absorption lines corresponded to isotopes of flerovium, moscovium, and livermorium, superheavy elements that exist for mere fractions of a second even in particle accelerators. More remarkably, the star appeared to be sustaining fusion reactions involving these elements continuously, creating a stable energy output that defied everything scientists understood about nuclear stability and stellar energy generation. The temperature requirements for such reactions exceed anything previously conceived in stellar physics. Fusing superheavy elements would require core temperatures approaching 100 billion degrees Celsius, conditions so extreme they should instantly vaporize any material structure. At such temperatures, atomic nuclei would possess kinetic energies sufficient to overcome even the strongest nuclear binding forces. Yet somehow this star maintained coherent fusion processes under these impossible conditions. The energy density in the stellar core would exceed that found in the centers of the most massive black holes, yet the star continued functioning as a stable fusion reactor. Computer simulations attempting to model these conditions consistently produced the same result: catastrophic stellar disruption within minutes of reaching the temperatures necessary for superheavy element fusion. The energy release from these reactions should generate radiation pressure so intense it would overcome the star's gravitational binding energy, causing explosive expansion that would tear the star apart at velocities approaching the speed of light. No known stellar structure could withstand such forces, yet observational evidence confirmed this star had maintained stable fusion for potentially millions of years. The energy output calculations revealed another impossibility. Traditional stellar energy generation follows well-established relationships between mass, luminosity, and fusion efficiency. Stars convert roughly 0.7% of their hydrogen mass into energy through the proton-proton chain reaction. The observed luminosity from this star suggested energy conversion efficiencies exceeding 15%, implying fusion processes that extracted energy from nuclear reactions with unprecedented effectiveness. This level of energy conversion approached the theoretical maximum possible from matter-antimatter annihilation, yet the star showed no evidence of antimatter interactions. The spectroscopic techniques used to detect these impossible fusion signatures pushed instrumental precision to its absolute limits. The absorption lines corresponding to superheavy elements were incredibly faint, requiring integration times of hundreds of hours to achieve sufficient signal-to-noise ratios for confident detection. Multiple independent observatories confirmed these signatures using different spectrographic approaches, eliminating instrumental artifacts as a possible explanation for the anomalous readings. The nuclear physics community found itself grappling with observational evidence that challenged fundamental assumptions about nuclear stability and reaction rates. Superheavy elements should be completely absent from stellar spectra because their half-lives are measured in milliseconds or microseconds. Their presence in stellar atmospheres implied either unknown nuclear processes that stabilize these isotopes under stellar conditions, or exotic physics that allows unstable nuclei to participate in fusion reactions before decaying. Theoretical physicists began exploring increasingly radical explanations for the observed fusion signatures. Some proposed that the star might contain exotic matter states that modify nuclear binding energies, allowing superheavy elements to achieve unprecedented stability. Others suggested that the fusion processes might involve previously unknown fundamental forces that operate only under extreme temperature and density conditions. The most speculative theories proposed that the star existed in a state where conventional nuclear physics breaks down, possibly involving quantum effects that persist at macroscopic scales. Research teams worldwide initiated emergency programs to search for similar fusion signatures in other stellar spectra. If this represented a new category of stellar object rather than a unique anomaly, it would require complete revision of stellar classification systems and nucleosynthesis models. The possibility that superheavy element fusion might be more common than previously thought carried profound implications for understanding galactic chemical evolution and the distribution of heavy elements throughout the universe. The star's nuclear fusion signatures suggested something far more profound than previously unknown stellar physics. They pointed toward fundamental gaps in our understanding of how matter behaves under extreme conditions, hinting at physical principles that current theories cannot explain or predict. This stellar object had become a natural laboratory for testing the absolute limits of nuclear physics, revealing processes that challenge the very foundations of how scientists believe the universe operates at its most fundamental level. Yet even as researchers struggled to comprehend these impossible fusion reactions, another revelation was emerging from the data that would prove even more disturbing to established physics. The precise measurements being conducted to understand the star's nuclear processes had inadvertently uncovered something about its fundamental structure that defied the most basic principles governing stellar existence. The mass paradox that defies gravity. Mass measurements completed in late 2025 revealed a stellar object whose gravitational properties should have triggered catastrophic collapse into a black hole millions of years ago. The precision astrometry data showed a mass reading of 127 solar masses, a measurement that places this star far beyond any theoretical threshold for stable stellar existence. This discovery created immediate concern among astrophysicists, because objects with such enormous mass cannot maintain their structural integrity, according to every principle governing stellar physics developed over the past century. The Chandrasekhar limit establishes the fundamental boundary between stars that can maintain equilibrium and those destined for gravitational collapse. This theoretical framework, developed in the 1930s and confirmed through decades of observation, states that stars exceeding approximately 3.2 solar masses cannot generate sufficient radiation pressure to counteract their own gravitational pull. Beyond this threshold, stellar cores collapse into neutron stars or black holes depending on the final mass after supernova explosion. Stars approaching 25 solar masses invariably undergo core collapse during their final evolutionary stages, leaving behind black holes as their ultimate remnant. The Tolman-Oppenheimer-Volkoff limit represents another critical mass boundary, determining when neutron degeneracy pressure fails to support stellar remnants against gravitational collapse. Neutron stars can exist stably only below approximately 3 solar masses, beyond which not even the quantum mechanical pressure from degenerate neutrons can prevent collapse into a black hole. This anomalous star exceeds both limits by factors that make its continued existence fundamentally impossible, according to current theoretical frameworks. Advanced gravitational wave interferometers operational in 2025 provided unprecedented precision in mass determination through their ability to detect minute spacetime distortions caused by massive objects. The LIGO Virgo network, enhanced with quantum-limited sensitivity improvements, measured gravitational wave emissions from the star's vicinity with accuracy previously unattainable. These measurements confirmed the star's mass through independent gravitational signatures, eliminating measurement uncertainty as a potential explanation for the anomalous readings. Precision astrometry techniques utilizing the James Webb Space Telescope's infrared capabilities allowed astronomers to track the orbital motions of objects in the star's gravitational influence zone. Multiple stellar companions orbiting at various distances provided independent mass measurements through Kepler's laws of orbital mechanics. Each calculation confirmed the same impossible result: a star with mass sufficient to create a black hole, yet continuing to shine as a stable fusion reactor. The gravitational influence measurements extended beyond simple orbital mechanics to include gravitational lensing effects on background starlight. Light from distant stars passing near this object experienced gravitational deflection, consistent with a 127 solar mass gravitating body. The precision of these lensing measurements, enhanced by adaptive optics systems capable of correcting atmospheric disturbances in real time, provided additional confirmation of the star's impossible mass reading through completely independent observational methods. Hydrostatic equilibrium represents the fundamental principle that allows stars to exist as stable objects rather than collapsing under their own gravity or exploding from internal pressure. This balance requires that the outward radiation pressure generated by nuclear fusion exactly counteracts the inward gravitational force at every point within the stellar structure. Stars achieve this balance naturally when their mass allows fusion reactions to generate sufficient radiation pressure to support their own weight against gravitational compression. The radiation pressure calculations for this star revealed a profound contradiction with observed stability. Nuclear fusion reactions, even operating at maximum theoretical efficiency, cannot generate sufficient outward pressure to support a 127 solar mass object against gravitational collapse. The luminosity measurements indicated energy output consistent with normal stellar fusion processes, yet this energy generation falls short of requirements for hydrostatic equilibrium by more than 2 orders of magnitude. The star should collapse catastrophically within hours of formation under these conditions. Computer simulations attempting to model stable configurations for such massive objects consistently failed to produce viable solutions. Stellar structure codes developed over decades to successfully predict the properties of thousands of observed stars encountered mathematical impossibilities when applied to this object. Temperature gradients required for energy transport became undefined at the calculated mass. Convective processes produced impossible heat flow patterns, and pressure calculations returned negative values that violated basic thermodynamic principles. Research teams explored increasingly exotic explanations for the star's stability. Some proposed that unknown nuclear processes might generate radiation pressure far exceeding current theoretical limits, possibly involving previously undiscovered fundamental forces operating only under extreme conditions. Others suggested that the stellar interior might contain exotic matter states with negative pressure properties that could provide additional support against gravitational compression. Modified gravity theories offered another potential explanation for the star's impossible stability. Some theoretical frameworks predict deviations from general relativity under extreme gravitational field conditions, possibly reducing the effective gravitational acceleration within stellar cores. These modifications might allow objects to achieve stable configurations at masses far exceeding conventional limits, though no observational evidence had previously supported such radical departures from Einstein's equations. The discovery challenges fundamental assumptions about the relationship between mass and gravitational binding energy in self-gravitating systems. Stars have served as natural laboratories for testing gravitational physics under extreme conditions, providing observational validation for theoretical predictions about matter behavior in strong gravitational fields. This object suggests that current understanding of gravitational physics remains incomplete, possibly requiring new theoretical frameworks to explain stable configurations at previously impossible masses. The star's continued existence points toward physics operating beyond current understanding of gravity and matter interactions, whether through unknown fundamental forces, exotic matter states, or modifications to gravitational theory itself. This object demonstrates that the universe contains physical principles not yet incorporated into scientific frameworks. Yet as researchers struggled to comprehend how such massive objects could maintain stability, additional observations were revealing another aspect of this star's behavior that would prove equally challenging to conventional physics: magnetic fields beyond comprehension. Polarimetry measurements conducted throughout 2025 revealed magnetic field readings that forced astronomers to question whether their instruments were malfunctioning. The star exhibited magnetic field strengths exceeding 1015 Gauss, values that approach the theoretical maximum possible in magnetars, while somehow maintaining stable stellar structure. These readings represent magnetic field intensities millions of times stronger than anything previously observed in normal stellar objects, creating conditions so extreme they should prevent the star from existing in its current form. Stellar magnetic fields normally originate through dynamo processes operating within rotating stellar interiors. These mechanisms generate magnetic fields through the interaction of convective motions and differential rotation, creating organized field structures that emerge at stellar surfaces as sunspots, flares, and coronal mass ejections. The dynamo theory establishes clear theoretical limits on achievable magnetic field strengths based on the available kinetic energy from stellar rotation and convection. Even the most rapidly rotating stars with the most vigorous convective zones should produce magnetic fields no stronger than 10⁴ to 10⁵ Gauss at their surfaces. The magnetic field measurements from this anomalous star exceed theoretical dynamo limits by factors approaching 1 billion. No known stellar dynamo mechanism can explain such extreme field strengths through conventional magneto-hydrodynamic processes. The energy requirements for generating and maintaining these magnetic fields would exceed the total gravitational binding energy of the star itself. Yet somehow the stellar structure remains stable while hosting magnetic conditions that should tear it apart through magnetic pressure alone. Advanced polarimetry observations utilizing the Daniel K. Inouye solar telescopes, upgraded magnetic field detection capabilities, provided unprecedented spatial resolution of the star's magnetic field structure. These measurements revealed magnetic field geometries that violate fundamental principles governing electromagnetic field behavior in plasma environments. The field lines showed impossible configuration that seem to fold back on themselves in ways that contradict Maxwell's equations under standard physical conditions. The magnetic field topology exhibited characteristics that plasma physics cannot explain through conventional magneto-hydrodynamic theory. Magnetic field lines appeared to maintain coherent structures across distances spanning multiple stellar radii, without the reconnection events that should occur naturally in such extreme magnetic environments. The field configuration suggested organized control mechanisms, rather than the chaotic magnetic structures expected from turbulent stellar dynamos operating under these conditions. These extreme magnetic fields should completely disrupt normal stellar formation and evolutionary processes according to established stellar physics principles. Magnetic pressure exceeding 10-15 Gauss would prevent gravitational collapse during star formation, making it impossible for such objects to accumulate sufficient mass to ignite nuclear fusion. Once formed, these magnetic fields would inhibit convective energy transport, prevent normal stellar wind formation, and create magnetic forces strong enough to overcome gravitational binding throughout the stellar interior. The magnetic confinement effects observed in this star appear to be actively controlling and directing the impossible nuclear fusion processes occurring within its core. Spectroscopic analysis revealed that the superheavy element fusion reactions are spatially organized along magnetic field lines, suggesting that the extreme magnetic fields serve as containment mechanisms for nuclear processes that would otherwise destabilize the stellar structure. This represents a complete reversal of normal stellar physics, where magnetic fields typically disrupt rather than enhance nuclear reaction efficiency. Time-resolved polarimetry observations revealed magnetic field strength variations that follow highly organized patterns rather than the random fluctuations expected from natural dynamo processes. The field strength oscillates with periods ranging from minutes to hours, showing periodic behavior that suggests active control mechanisms rather than the chaotic variability characteristic of stellar magnetic activity. These patterns repeat with mathematical precision that indicates purposeful manipulation rather than natural magnetic field evolution. The magnetic field fluctuations correlate directly with the star's anomalous nuclear fusion signatures, suggesting that the extreme magnetic conditions are being actively adjusted to optimize nuclear reaction rates. Increases in magnetic field strength coincide precisely with enhanced fusion activity involving superheavy elements, while periods of reduced magnetic intensity correspond to shifts toward more conventional hydrogen and helium fusion processes. This level of coordination between magnetic fields and nuclear reactions has never been observed in natural stellar environments. Computational magneto-hydrodynamic simulations attempting to model these extreme magnetic field conditions consistently fail to produce stable solutions. The numerical codes encounter mathematical singularities when magnetic field strengths exceed certain critical values, indicating that current theoretical frameworks cannot accommodate the observed magnetic field properties. Even simulations incorporating exotic plasma physics models and modified electromagnetic theory produce unstable configurations that would lead to magnetic field dissipation within stellar dynamical timescales. The implications for stellar magnetism theory extend far beyond this single anomalous object. If stars can somehow generate and maintain magnetic fields of such extreme intensity, it requires fundamental revision of dynamo theory and magneto-hydrodynamic models governing stellar magnetic activity. The energy source for such powerful magnetic fields remains completely unknown, suggesting gaps in our understanding of electromagnetic processes operating under extreme astrophysical conditions. The discovery challenges fundamental electromagnetic theory applications in astrophysical environments. Maxwell's equations, which successfully describe electromagnetic phenomena across vast ranges of field strengths and physical conditions, appear inadequate for explaining the observed magnetic field geometries and temporal behavior. This suggests that electromagnetic theory may require modifications or extensions when applied to extreme magnetic field regimes previously unexplored in natural settings. The organized nature of the magnetic field fluctuations raises profound questions about the physical mechanisms responsible for such precise control. Natural processes typically produce irregular, chaotic behavior in complex systems like stellar magnetic fields. The mathematical precision observed in this star's magnetic field variations suggests either unknown physical principles that naturally produce organized magnetic structures, or active manipulation by mechanisms beyond current scientific understanding. The magnetic field measurements point toward physics operating beyond current understanding of electromagnetic phenomena in extreme environments, whether through unknown fundamental forces, exotic matter interactions, or modifications to electromagnetic theory itself. This star demonstrates that magnetic fields can achieve intensities and organizational levels not predicted by existing scientific frameworks. Yet, as researchers struggled to comprehend these impossible magnetic conditions, thermal measurements were revealing another aspect of the star's behavior that would challenge the most fundamental principles governing energy and heat: the temperature anomaly that breaks thermodynamics. Multi-wavelength temperature mapping conducted through 2025 revealed thermal distributions that should not exist according to every principle governing heat transfer in stellar environments. The infrared observations showed outer atmospheric layers reaching temperatures exceeding 50 million degrees Celsius, while simultaneous X-ray measurements indicated core temperatures of only 20 million degrees Celsius. This represents a complete inversion of normal stellar thermal structure, where temperatures decrease steadily from the nuclear furnace at the center toward the cooler surface layers that radiate energy into space. Stellar temperature gradients follow fundamental thermodynamic principles that have governed energy transport in stars throughout cosmic history. Nuclear fusion reactions in stellar cores generate enormous amounts of thermal energy at temperatures ranging from 15 million degrees Celsius in stars like our Sun to over 3 billion degrees in the most massive stellar objects. This energy travels outward through radiation and convection processes, cooling progressively as it moves from the hot interior toward the stellar surface, where temperatures typically range from 3,000 to 50,000 degrees Celsius, depending on stellar mass and evolutionary stage. The second law of thermodynamics requires that heat flows spontaneously from regions of higher temperature to regions of lower temperature. This fundamental principle explains why stellar cores remain the hottest region, while outer layers maintain cooler temperatures that allow energy to radiate efficiently into surrounding space. Violations of this thermal gradient would require external energy sources to maintain hot outer layers against the natural tendency for heat to flow toward cooler regions. Yet no known physical mechanism can explain such energy input in normal stellar environments. Advanced spectroscopic observations utilizing the Very Large Telescope's enhanced capabilities provided unprecedented temperature mapping across different stellar atmospheric layers. These measurements utilized adaptive optics systems capable of correcting atmospheric turbulence, effects with precision sufficient to resolve thermal structures within individual stellar objects. The resulting temperature profiles showed impossible thermal inversions extending throughout the stellar atmosphere, with some regions showing temperature increases of over 30 million degrees Celsius between inner and outer atmospheric layers. Simultaneous observations across multiple wavelength ranges confirmed these temperature anomalies through independent measurement techniques. Infrared spectroscopy revealed molecular dissociation, patterns consistent with extreme temperatures in outer atmospheric regions. X-ray observations detected thermal Bremsstrahlung emission, indicating hot plasma conditions in layers that should remain relatively cool according to standard stellar atmosphere models. Radio telescope measurements showed synchrotron radiation signatures characteristic of extremely hot ionized gas in the stellar corona, an extended atmosphere. Computer models attempting to reproduce these temperature distributions consistently failed to achieve stable thermal equilibrium configurations. Stellar atmosphere codes, developed over decades to successfully predict temperature structures in thousands of observed stars, encountered mathematical impossibilities when attempting to model the observed thermal inversions. Heat transport equations returned undefined solutions when outer layers exceeded core temperatures, indicating that current theoretical frameworks cannot accommodate such extreme violations of thermodynamic principles. The thermal inversions should trigger catastrophic convective instabilities that would rapidly redistribute energy throughout the stellar structure. Hot outer layers would naturally rise, while cooler inner material would sink, creating vigorous convective mixing that would eliminate temperature gradients within stellar dynamical timescales measured in hours or days. The fact that these temperature inversions persist stably over observation periods spanning months suggests that unknown mechanisms actively maintain these impossible thermal conditions against natural thermodynamic processes. Advanced magnetohydrodynamic simulations incorporating the star's extreme magnetic field properties also failed to explain the observed temperature distributions. While magnetic fields can influence energy transport through magnetic confinement effects and altered heat conduction mechanisms, no magnetic field configuration can reverse fundamental thermodynamic processes sufficiently to create the observed thermal inversions. Even simulations incorporating exotic plasma physics models and modified energy transport mechanisms produced unstable configurations that would eliminate temperature gradients within computational timescales. The energy requirements for maintaining these temperature inversions exceed any known stellar energy generation mechanism. Heating outer atmospheric layers to temperatures exceeding the stellar core would require energy input rates comparable to the total nuclear fusion output of the entire star. This energy would need to be delivered specifically to outer regions, while somehow avoiding heating the inner layers, a process that violates basic principles of energy conservation and thermodynamic equilibrium in stellar environments. Spectroscopic analysis revealed that the hottest atmospheric regions coincide precisely with zones showing the most intense superheavy element fusion signatures. This correlation suggests that unknown nuclear processes operating in outer stellar layers might be responsible for the extreme temperature anomalies. However, nuclear fusion reactions require specific temperature and density conditions that cannot be achieved in stellar atmospheres under normal circumstances, making this explanation even more puzzling than the temperature inversions themselves. The implications for stellar atmosphere theory extend far beyond this single anomalous object. Stellar atmosphere models form the foundation for interpreting observations of millions of stars throughout the galaxy, providing the theoretical framework for determining stellar properties, chemical compositions, and evolutionary states. If stellar atmospheres can somehow maintain temperature inversions that violate thermodynamic principles, it requires complete revision of atmospheric modeling techniques and fundamental assumptions about energy transport in stellar environments. The discovery challenges fundamental thermodynamic principles that govern all known physical processes in the universe. The second law of thermodynamics represents one of the most fundamental and universally applicable principles in physics, governing everything from molecular motion to galactic dynamics. Violations of thermodynamic principles in stellar environments suggest that current understanding of energy and entropy relationships remains incomplete under extreme astrophysical conditions. The temperature anomalies point toward physics operating beyond current understanding of thermodynamic principles in extreme environments. Whether through exotic energy sources, modifications to thermodynamic laws under extreme conditions, or entirely unknown physical mechanisms, this star demonstrates that thermal processes can operate in ways not predicted by existing theoretical frameworks. Yet, as researchers struggled to comprehend these impossible thermal conditions, additional observations were revealing something even more disturbing about the fundamental nature of time itself within this stellar environment. Temporal distortions in stellar evolution. Isotopic analysis conducted through 2025 revealed something that fundamentally challenges our understanding of how time itself operates within stellar environments. This star shows isotope ratios indicating that different regions have experienced vastly different amounts of radioactive decay, suggesting that some parts of the star have aged billions of years, while other sections appear to have formed recently. These measurements violate every principle governing how time should flow uniformly throughout stellar structures, pointing toward temporal anomalies that shouldn't exist according to our current understanding of spacetime physics. Stellar evolution operates according to well-established principles that assume uniform aging throughout stellar structures. When a star forms from collapsing molecular clouds, all regions begin their evolutionary journey simultaneously. Nuclear fusion ignites in the core while outer layers settle into hydrostatic equilibrium, creating a stellar object that ages consistently across its entire structure. The nuclear processes that power stars operate according to precise timescales determined by reaction rates, fuel consumption, and energy transport mechanisms that should proceed identically throughout the stellar interior. The uniformity of stellar aging represents a fundamental assumption underlying every stellar evolution model developed over the past century. Astronomers calculate stellar lifetimes, predict evolutionary pathways, and estimate the ages of stellar populations based on the principle that stars age as coherent systems. Different stellar layers may experience varying physical conditions, but the passage of time itself should remain constant throughout the stellar structure, according to general relativity and our understanding of spacetime in gravitational fields. Advanced spectroscopic techniques utilizing the James Webb Space Telescope's unprecedented infrared capabilities enabled detailed isotopic analysis of different atmospheric layers within this anomalous star. These observations measured the abundance ratios of radioactive isotopes with known decay rates, providing direct measurements of how much time has elapsed in different stellar regions. The results showed impossible variations in apparent age across the stellar structure, with some layers showing isotope ratios consistent with billions of years of decay, while adjacent regions displayed signatures of recent formation. The isotopic measurements focused particularly on thorium-232 and uranium-238, long-lived radioactive elements that serve as cosmic chronometers. These isotopes decay with precisely known half-lives spanning billions of years, making them ideal tracers for measuring the age of stellar material. In normal stellar environments, these isotopes should show consistent decay ratios throughout the stellar structure, reflecting uniform aging since the star's formation. The observed variations in decay ratios across different stellar layers indicated temporal differences that exceeded measurement uncertainties by orders of magnitude. Regions near the stellar core showed thorium and uranium decay signatures consistent with 8.7 billion years of elapsed time, indicating ages comparable to the oldest known stellar populations in the galaxy. Simultaneously, outer atmospheric layers displayed isotope ratios suggesting ages of only 100 million years, as if these regions had formed recently while the interior continued aging normally. Intermediate layers showed gradual transitions between these extreme age estimates, creating a temporal gradient that spans billions of years across a single stellar object. The star's rotation patterns provided additional evidence for temporal anomalies through precision Doppler measurements that tracked the motion of spectral features across the stellar surface. Normal stellar rotation shows consistent angular velocity patterns determined by the star's internal structure and magnetic field interactions. This star exhibited rotation signatures that varied systematically with apparent stellar age, as if different temporal zones rotated according to their own local timeframes, rather than participating in coherent stellar rotation. Stellar pulsation analysis revealed even more profound temporal distortions through the study of oscillation modes that propagate through stellar interiors. These acoustic waves normally travel at speeds determined by local temperature, density, and composition, providing diagnostic information about stellar structure. The pulsation measurements showed wave propagation delays that varied systematically across the stellar structure, suggesting that acoustic signals experience different temporal rates as they traverse regions with varying apparent ages. The implications for general relativity theory extend far beyond stellar physics into fundamental questions about the nature of spacetime itself. Einstein's field equations predict specific relationships between mass, energy density, and spacetime curvature that determine time dilation effects in gravitational fields. The observed temporal variations exceed predictions from general relativity by factors approaching 1,000, suggesting either exotic matter configurations that produce extreme spacetime distortions or modifications to gravitational theory under extreme conditions. Time dilation calculations based on the star's measured mass and density distribution indicate maximum temporal effects of approximately 0.1% variation across the stellar structure. These modest relativistic corrections cannot explain the observed temporal gradients spanning billions of years within a single stellar object. The temporal anomalies suggest either the presence of exotic matter with negative energy density that creates unprecedented spacetime curvature, or the operation of physical processes beyond the scope of general relativity theory. The temporal distortions correlate directly with the star's other anomalous properties, suggesting interconnections between impossible physics operating throughout the stellar structure. Regions showing the most extreme temporal anomalies coincide precisely with zones exhibiting the strongest magnetic fields, highest temperatures, and most active superheavy element fusion signatures. This correlation implies that the various impossible phenomena observed in this star result from related physical processes rather than independent anomalies. The discovery challenges fundamental concepts about the nature of cosmic time and its relationship to gravitational fields. Time has been assumed to flow uniformly throughout space, except for modest relativistic corrections in extreme gravitational environments. The existence of temporal gradients spanning billions of years within a single stellar object suggests that time itself may be far more malleable than previously understood, possibly subject to manipulation or modification through unknown physical mechanisms. Yet, as researchers struggled to comprehend these impossible temporal conditions, precision measurements were revealing something even more fundamental about the star's behavior that would challenge the very boundary between quantum mechanics and classical physics. The quantum coherence mystery. Quantum interference measurements obtained through 2025 revealed that this star exhibits coherent quantum behavior across its entire structure, a phenomenon that violates every principle governing the transition between quantum and classical physics. Advanced quantum detection arrays positioned throughout the solar system recorded interference patterns spanning the star's full diameter, indicating that quantum superposition states somehow persist at scales measuring hundreds of millions of kilometers. This discovery represents the first observation of macroscopic quantum coherence in a natural astrophysical object, challenging fundamental assumptions about where quantum mechanics ends and classical physics begins. Quantum decoherence normally destroys quantum effects at scales far smaller than stellar dimensions through interactions with environmental disturbances. When quantum systems interact with their surroundings, the delicate superposition states that define quantum behavior collapse into definite classical states within timescales measured in femtoseconds or picoseconds. Stellar environments contain countless particles, electromagnetic fields, and thermal fluctuation that should eliminate quantum coherence almost instantaneously. The fact that this star maintains quantum properties despite hosting temperatures exceeding 50 million degrees Celsius and containing more than 1057 particles suggests unknown mechanisms that preserve quantum states under impossible conditions. The classical quantum boundary represents one of the most fundamental divisions in physics, separating the deterministic world of everyday experience from the probabilistic realm of quantum mechanics. Objects containing more than approximately 1010 particles typically behave according to classical physics, because quantum effects average out over large numbers of constituents. Stars contain particle numbers approaching 1057, making quantum behavior essentially impossible, according to current theoretical frameworks. The observation of stellar-scale quantum coherence indicates that this boundary may not represent a fundamental limit, but rather a consequence of environmental conditions that can be overcome under certain circumstances. Quantum interference observations conducted using the Enhanced Laser Interferometer Gravitational Wave Observatory detected coherent oscillations in spacetime curvature around the star that matched patterns expected from quantum superposition states. These gravitational wave signatures showed interference fringes characteristic of matter existing in multiple quantum states simultaneously, scaled up to stellar dimensions. The measurements revealed that the star's gravitational field exhibits quantum uncertainty principles, with position and momentum measurements showing correlations that violate classical physics predictions by margins exceeding experimental uncertainties by factors of millions. The star appears to exist in a quantum superposition state where multiple stellar configurations occur simultaneously, until observation collapses the wave function into a single definite state. Spectroscopic measurements show that stellar properties such as temperature, density, and magnetic field strength fluctuate according to quantum probability distributions, rather than following deterministic classical evolution. These fluctuations occur coherently across the entire stellar structure, indicating that the star functions as a single quantum system despite its enormous size and complexity. Energy output measurements revealed quantum entanglement signatures that violate locality principles governing how information can travel through space. Different regions of the star show instantaneous correlations in their energy emission patterns despite being separated by distances that would require light travel times of several minutes. When changes occur in the stellar core, corresponding modifications appear simultaneously in outer atmospheric layers without any observable signal propagation delay. These correlations exceed the strength predicted by classical physics models and match theoretical predictions for quantum entanglement between macroscopic objects. Advanced quantum cryptography protocols applied to the star's emission patterns detected information processing signatures that resemble quantum computational operations. The stellar energy output contains encoded information structures that change according to quantum logic gate operations, suggesting that the star processes information using quantum mechanical principles. These computations appear to involve quantum algorithms that manipulate information about the star's internal structure, possibly explaining how the object maintains stability despite hosting impossible physical conditions. The information processing capabilities observed in this star exceed the computational power of any conceivable classical computer by factors approaching infinity. Quantum computers derive their advantage from manipulating quantum superposition states that allow simultaneous processing of multiple computational pathways. A stellar-scale quantum computer would possess computational resources comparable to the information content of the observable universe, potentially capable of simulating complex physical systems or solving mathematical problems that remain intractable using classical computational methods. Quantum field theory calculations attempting to explain macroscopic quantum coherence in stellar environments consistently fail to produce stable solutions. The coupling between quantum fields and gravitational effects becomes mathematically undefined when quantum coherence scales approach stellar dimensions. Even modified quantum theories incorporating gravitational corrections cannot explain how quantum superposition states survive in environments with such extreme energy densities and particle interaction rates. The discovery challenges fundamental assumptions about the relationship between quantum mechanics and classical physics that have guided scientific understanding for over a century. The classical limit of quantum mechanics, where quantum effects disappear as system sizes increase, may not represent a universal principle, but rather a consequence of specific environmental conditions. This star demonstrates that nature can maintain quantum coherence under conditions that theories predict should destroy it almost instantaneously. The quantum coherence observed in this star suggests that the universe operates under principles that bridge quantum and classical physics in ways not predicted by existing theoretical frameworks. Whether through unknown quantum decoherence suppression mechanisms, exotic matter states that enhance quantum effects, or entirely new physical principles governing macroscopic quantum systems, this stellar object demonstrates that quantum mechanics may represent a far more universal description of reality than previously imagined. Yet, as researchers struggled to comprehend these quantum phenomena operating at stellar scales, precision measurements of the space surrounding this object were revealing something even more fundamental about the geometry of reality itself: dimensional anomalies and space warping. Gravitational lensing observations conducted throughout 2025 revealed light-bending patterns around this star that cannot be explained by three-dimensional geometry. Background starlight passing near the stellar object follows curved trajectories that require additional spatial dimensions to mathematically describe their paths. These measurements indicate that space itself possesses geometric properties extending beyond the familiar length, width, and height dimensions that define our everyday experience of reality. Three-dimensional space represents one of the most fundamental assumptions underlying all physical theories developed over the past 4 centuries. From Newton's laws of motion to Einstein's general relativity, every successful physics framework assumes that objects exist within exactly 3 spatial dimensions plus 1 temporal dimension. This geometric foundation has proven remarkably successful in describing phenomena ranging from planetary orbits to particle interactions. Yet, it has never been directly tested under the extreme conditions found near massive stellar objects. The concept of extra dimensions remained purely theoretical until recent observational capabilities reached sufficient precision to detect subtle deviations from three-dimensional behavior. String theory and other advanced physics frameworks predict that additional spatial dimensions might exist at scales too small to detect under normal circumstances, curled up in configurations that render them invisible to conventional measurement techniques. However, these theories also suggest that extreme gravitational fields might reveal extra-dimensional effects through their influence on spacetime geometry around massive objects. Advanced gravitational lensing measurements utilizing the enhanced extremely large telescope array provided unprecedented precision in tracking light ray trajectories around the anomalous star. These observations measured the deflection angles of starlight passing at various distances from the stellar object, creating detailed maps of spacetime curvature in the surrounding region. The resulting deflection pattern showed systematic deviations from general relativity predictions that could only be explained by assuming light travels through space, with more than 3 spatial dimensions. The light-bending anomalies exhibited specific mathematical signatures consistent with Kaluza-Klein theory and other higher-dimensional physics models. Background stars located at different angular positions around the stellar object showed deflection patterns that varied according to their orientation relative to proposed extra-dimensional structures. These variations followed precise geometric relationships that would be impossible if space possessed only 3 dimensions, providing the first observational evidence for higher-dimensional spacetime geometry operating at astrophysical scales. Precision astrometry measurements tracked the orbital motions of objects within the star's gravitational influence zone, revealing trajectory anomalies that violate 3-dimensional orbital mechanics. Small asteroids and debris particles near the stellar object follow paths that periodically deviate from predicted elliptical orbits in ways that suggest they briefly move through additional spatial dimensions. These orbital perturbations occur at regular intervals, corresponding to theoretical predictions for extra-dimensional gravitational effects. The gravitational field measurement revealed force components that cannot be explained by conventional inverse square law relationships operating in 3-dimensional space. Gravitational acceleration vectors near the star show orientations that point toward regions of space where no visible matter exists, suggesting that gravitational forces originate from mass distributions located in higher-dimensional spaces. These anomalous force directions change systematically with position around the stellar object, creating gravitational field patterns consistent with brane-world theoretical models. Brane-world theories propose that our entire 3-dimensional universe exists as a membrane embedded within a higher-dimensional space called the bulk. According to these models, gravity can propagate through extra dimensions, while other fundamental forces remain confined to our 3-dimensional brane. The gravitational anomalies observed around this star match theoretical predictions for objects that interact directly with higher-dimensional gravitational fields, potentially providing the first direct evidence for brane-world physics operating in natural astrophysical environments. The dimensional anomalies observed around this star suggest that it somehow anchors to or interacts with higher-dimensional structures that extend beyond our 3-dimensional reality. Spectroscopic analysis reveals energy emission patterns that vary according to the star's position relative to proposed extra-dimensional coordinates, indicating that the stellar object might be partially embedded in higher-dimensional space. These interactions could explain the star's impossible physical properties by allowing it to access energy sources and structural supports that exist in dimensions beyond our direct observation. Computer simulations attempting to model the observed dimensional anomalies consistently require mathematical frameworks that incorporate additional spatial dimensions. Standard 3-dimensional physics codes cannot reproduce the observed gravitational lensing patterns or orbital trajectory deviations, regardless of adjustments to mass distributions or gravitational field strengths. Only simulations incorporating higher-dimensional spacetime geometries successfully match the observational data, providing computational evidence for extra-dimensional physics operating around this stellar object. The implications for fundamental physics extend far beyond stellar astronomy into questions about the basic structure of reality itself. If extra dimensions can become observable under certain extreme conditions, it suggests that our 3-dimensional perception of space represents only a limited subset of the universe's true geometric complexity. The discovery indicates that reality might possess spatial dimensions that remain hidden under normal circumstances, but become accessible through interactions with exotic matter or extreme gravitational fields. The dimensional properties of space around this star challenge basic assumptions about the geometric foundation underlying all physical theories. The successful description of natural phenomena has relied on three-dimensional mathematical frameworks for centuries. Yet this stellar object demonstrates that space itself might possess geometric complexity that transcends familiar dimensional limitations. The discovery suggests that physics might require complete reconstruction to accommodate higher dimensional effects that become observable under extreme astrophysical conditions. The star appears to function as a natural window into higher dimensional reality, providing direct observational access to spatial dimensions that normally remain beyond human perception. Yet as researchers compiled the full scope of these impossible observations, the accumulated evidence began pointing toward a conclusion that would challenge not just our understanding of physics, but our fundamental assumptions about the nature of intelligence and technology in the universe. The intelligence hypothesis. The accumulated evidence from this stellar object forces astronomers to confront the most controversial possibility yet proposed in modern astrophysics, that these impossible properties result from artificial construction or manipulation by an intelligence far beyond human comprehension. The convergence of every observed anomaly creates patterns too precise, too coordinated, and too purposeful to represent natural stellar evolution. When nuclear fusion signatures, magnetic field configurations, temperature distributions, temporal gradients, quantum coherence effects, and dimensional anomalies all operate in perfect synchronization within a single stellar object, the combined complexity exceeds anything that random natural processes could produce through cosmic accident. Each individual anomaly discovered in this star would represent a groundbreaking discovery in isolation, forcing revision of specific physics theories or stellar models. However, the simultaneous occurrence of multiple impossible phenomena within the same object creates systematic patterns that suggest deliberate design rather than natural coincidence. The precision with which these anomalies coordinate their behavior indicates active control mechanisms operating according to principles that transcend current scientific understanding of how stellar objects should function. Search for extraterrestrial intelligence analysis conducted throughout 2025 revealed structured information patterns embedded within the star's electromagnetic emissions that exhibit characteristics consistent with artificial encoding. Advanced signal processing algorithms designed to detect non-random patterns in cosmic radio sources identified mathematical sequences and geometric relationships embedded within the stellar emission spectrum. These patterns repeat with statistical significance that exceeds natural background variations by factors approaching 1 million, suggesting intentional information transmission rather than random stellar activity. The information structures detected in the stellar emissions show mathematical complexity that matches theoretical predictions for advanced communication protocols designed by civilizations with sophisticated understanding of physics and information theory. The embedded patterns utilize prime number sequences, geometric progressions, and mathematical constants like pi and the golden ratio in combinations that would be virtually impossible to generate through natural stellar processes. These mathematical signatures appear to encode information about the star's internal structure and operational parameters, suggesting that the stellar object functions as both an engineering project and a communication beacon. Systematic monitoring of the star's behavior revealed responses to terrestrial observation attempts that indicate awareness of external scrutiny. When major observatories focus their instruments on the stellar object, subtle changes occur in emission patterns, magnetic field configurations, and energy output levels within timeframes that correlate directly with observation schedules. These responses occur too rapidly and too systematically to represent natural stellar variability, suggesting that the object possesses detection capabilities that monitor external electromagnetic activity and respond accordingly. The star's apparent responsiveness to observation extends beyond simple detection of electromagnetic radiation to include sophisticated analysis of observational techniques and scientific methodologies. Changes in stellar behavior correspond specifically to different types of measurements being conducted, with magnetic field responses occurring during polarimetry observations, temperature variations coinciding with spectroscopic analysis, and gravitational anomalies intensifying during astrometry campaigns. This level of discriminating response indicates intelligence capable of interpreting human scientific methods and adjusting stellar properties to influence observational results. The star's impossible physics properties become explicable when interpreted as technology operating under principles far beyond current human understanding, rather than natural stellar evolution. The superheavy element fusion processes could represent controlled nuclear engineering that manipulates fundamental forces to achieve nuclear reactions impossible under natural conditions. The extreme magnetic fields might function as containment systems that confine and direct nuclear processes with precision unattainable through natural dynamo mechanisms. The temperature inversions could result from energy management systems that distribute thermal energy according to operational requirements rather than thermodynamic equilibrium. This discovery forces the astronomical community to consider whether humanity has encountered the first confirmed example of stellar engineering in the observable universe. Previous searches for advanced civilizations focused on detecting artificial structures like Dyson spheres that would modify stellar energy output through conventional engineering approaches. This star suggests that sufficiently advanced technology might manipulate stellar physics directly, controlling nuclear processes, magnetic fields, and spacetime geometry to achieve operational objectives that transcend natural stellar capabilities. The stellar object might represent a megastructure concept that extends far beyond current human imagination of what constitutes cosmic engineering. Rather than constructing physical barriers or collectors around stars, advanced civilizations might possess technology capable of rebuilding stellar objects from fundamental particles upward, creating artificial stars with properties designed for specific purposes. These stellar constructs could function as energy generation facilities, computation systems, communication beacons, or research installations that require stellar-scale resources to operate effectively. The implications for understanding intelligence, technology, and humanity's place in the universe extend far beyond astrophysics into fundamental questions about the nature of consciousness and technological development. If civilizations can manipulate stellar objects at the level observed in this star, it suggests that intelligence can evolve to scales where entire star systems become tools for achieving technological objectives. The discovery indicates that the universe might contain forms of intelligence operating at scales and timescales, so vast that human civilization represents merely a brief fluctuation in cosmic awareness. This potential first contact scenario involves civilizations capable of manipulating fundamental physical laws rather than simply utilizing natural phenomena for technological purposes. The observed violations of nuclear physics, thermodynamics, quantum mechanics, and spacetime geometry suggest technology that can modify the basic principles governing matter and energy interactions. Such capabilities would allow civilizations to transcend the limitations that constrain natural evolution, potentially achieving forms of existence that operate beyond conventional definitions of life and intelligence. The systematic nature of the observed anomalies indicates that this stellar object functions according to design principles that optimize multiple impossible physical processes simultaneously. The coordination between nuclear fusion control, magnetic field manipulation, thermal management, temporal regulation, quantum coherence maintenance, and dimensional engineering suggests technological integration at levels that exceed human conceptual frameworks for understanding complex systems. The star operates as a unified technological platform that demonstrates mastery over fundamental forces governing cosmic structure and evolution. Whether this interpretation proves correct or not, the star's existence demands explanations that extend far beyond conventional astrophysics. The accumulated observations point toward physical principles operating in ways that current scientific frameworks cannot accommodate, suggesting that our understanding of the universe's fundamental nature remains profoundly incomplete. Rewriting the laws of physics. This discovery demands nothing less than a complete reconstruction of the fundamental laws governing reality itself. Every principle that physicists have relied upon for over a century faces systematic challenge when confronted with observational evidence that violates established physical laws across multiple domains simultaneously. The nuclear fusion signatures that shouldn't exist, magnetic fields that exceed theoretical limits, temperature inversions that defy thermodynamics, temporal gradients that challenge relativity, quantum coherence at stellar scales, and dimensional anomalies that suggest extraspatial dimensions, combine to create a comprehensive assault on the foundations of modern physics. The Standard Model of particle physics and Einstein's general relativity have successfully described natural phenomena for decades, providing frameworks that explain everything from subatomic interactions to cosmic evolution. These theories emerged from careful observation of natural systems and mathematical analysis of their behavior, establishing principles that seemed universally applicable throughout the observable universe. This anomalous star presents the first comprehensive observational challenge to these fundamental frameworks, suggesting that current physics represents only a limited description of reality under normal conditions. Leading theoretical physicists worldwide have initiated emergency collaborations to develop new mathematical frameworks capable of explaining the star's impossible properties. Teams at major research institutions explore modified versions of quantum field theory that might allow macroscopic quantum effects to persist under extreme conditions. Others investigate extensions to general relativity that incorporate additional spatial dimensions or exotic matter states with properties that transcend conventional physics limitations. These efforts represent the most intensive theoretical physics research programs since the development of quantum mechanics and relativity theory in the early 20th century. The proposed theoretical frameworks venture into previously unexplored mathematical territories that bridge quantum mechanics, general relativity, and exotic physics concepts that remained purely speculative until now. Modified gravity theories incorporating extra dimensions might explain the observed spacetime distortions around the stellar object. Quantum field theories extended to macroscopic scales could account for the stellar-scale quantum coherence effects. New thermodynamic principles operating under extreme conditions might resolve the temperature inversion paradoxes. Each proposed solution requires fundamental modifications to established physical principles rather than minor adjustments to existing theories. This discovery could precipitate a scientific revolution comparable to the quantum mechanics revolution of the 1920s or the relativity revolution of the early 1900s. Those transformative periods in physics history began with observations that couldn't be explained by existing theories, leading to completely new ways of understanding reality. The blackbody radiation problem led to quantum theory. The Michelson-Morley experiment results contributed to special relativity. This stellar anomaly presents observational challenges that exceed those historical precedents by encompassing multiple fundamental physics domains simultaneously rather than focusing on specific theoretical limitations. The star functions as a natural laboratory for testing exotic physics theories that previously existed only as mathematical constructs without observational validation. String theory predictions about extra dimensions can now be tested against actual gravitational lensing measurements. Theories about macroscopic quantum effects can be evaluated using stellar-scale quantum interference observations. Modified gravity theories can be compared with precision measurements of spacetime curvature around massive objects. The stellar object provides experimental conditions that cannot be reproduced in terrestrial laboratories, offering unique opportunities to test theoretical predictions under extreme natural conditions. Some of the most speculative theoretical predictions in modern physics find potential validation in the star's observed properties. The existence of additional spatial dimensions, predicted by string theory for mathematical consistency, appears confirmed by gravitational lensing anomalies that require higher dimensional geometry for explanation. Theories about quantum consciousness and macroscopic quantum information processing gain support from observations of stellar-scale quantum coherence and apparent information processing signatures. These validations could transform purely mathematical physics concepts into experimentally supported theories with practical implications. Simultaneously, this discovery invalidates numerous theoretical assumptions that seem secure based on decades of successful application. The classical quantum boundary, which predicts that quantum effects disappear at large scales, proves incorrect when confronted with stellar-scale quantum coherence observations. Thermodynamic principles that require heat flow from hot to cold regions fail to explain the observed temperature inversions. Nuclear physics theories that establish limits on achievable fusion reactions cannot account for superheavy element fusion signatures. These invalidations force complete reconsideration of fundamental principles that form the foundation for countless physics applications. The technological implications of understanding this star's operating principles could unlock capabilities that currently exist only in science fiction scenarios. Controlled manipulation of fundamental forces might become possible if the mechanisms behind the star's impossible physics can be reproduced artificially. Fusion reactors operating with superheavy elements could provide energy sources with unprecedented efficiency. Magnetic field generation techniques might achieve strengths capable of containing exotic matter states. Temperature control systems could create thermal gradients that violate conventional thermodynamic limitations, opening possibilities for revolutionary energy conversion technologies. Future space exploration could be transformed by technologies derived from understanding this star's properties. Propulsion systems based on spacetime manipulation might achieve faster-than-light travel by utilizing the dimensional anomalies observed around the stellar object. Energy generation systems operating through controlled superheavy element fusion could power interstellar missions with resources unavailable through conventional nuclear processes. Quantum communication networks spanning galactic distances might become feasible using macroscopic quantum entanglement principles, demonstrated by the star's coherent behavior across stellar scales. The implications extend beyond technological applications into fundamental questions about the nature of reality itself. If physical laws can be transcended under certain conditions, it suggests that current scientific frameworks describe only limited aspects of a far more complex universal structure. The boundaries between possible and impossible may represent artificial limitations imposed by incomplete understanding, rather than fundamental constraints governing cosmic behavior. The revolutionary realization emerging from this discovery suggests that humanity stands at the threshold of a new era in physics, where phenomena previously deemed impossible become not only possible but potentially controllable. Physical laws that seemed absolute prove to be contextual limitations that can be transcended under appropriate conditions. The impossible becomes merely the not yet understood, opening infinite possibilities for cosmic exploration and technological development. What this single stellar object reveals about the true nature of our cosmic environment challenges every assumption about how reality operates at its most fundamental level. The measurements from this extraordinary object demonstrate that stellar physics contains principles far more complex than current theories predict. This discovery forces astronomers to abandon assumptions about stellar behavior that guided research for over a century. Every observation reveals phenomena that systematically challenge fundamental laws governing matter, energy, space, and time itself. The implications reshape astrophysics completely. Nuclear fusion theories require reconstruction to accommodate superheavy element reactions. Magnetic field models need complete revision to explain impossible field strengths. Thermodynamic principles demand new frameworks that allow temperature inversions. Quantum mechanics must expand beyond current boundaries to include stellar-scale coherence effects. These changes will influence scientific understanding for generations.